Our first talk for today is by Jean-Philippe Chassé from University de Montreal, and he will tell us about convergence and Riemannian bounds for Lagrangian submanifolds.
Well, thank you for the introduction. Well, it's an honor to start the seminar for this year. I hope I'll be worthy of this honor. So today, what I want to talk is kind of like, well, it kind of in some sense is simple problematic. So the setup is as follows. So suppose that you have some metric D, right? D is a metric between like it's a metric on spaces of Lagrangians. So you should imagine the Lagrangian Hofer metric on some Lagrangian orbit, or the spectral norm on some set of Lagrangians, or one of these new shadow metrics introduced by Biran, Cornea, and Shelukhin. Okay? So you have one of these metrics, and you're wondering essentially, what does it mean for a sequence to converge in one of those metrics? Or equivalently, what's the topology that it induces on the space? And so how our written is that, well, can we say something? So say that Ln is converging to some L0, and I know that L0 is some embedded Lagrangian, then can I relate Ln to L0 for n large enough? So essentially, what can I say about the neighborhood of L0? So the idea to find out about that would be, well, if for some reason the sequence happens to converge in Hausdorff metric, so in this set-theoretic sense, then I know that well the Hausdorff metric is simple, it's nice, so it preserves a lot of like topological properties. So I know that like let's say Ln and L0 will have the same number of connected components for Ln large enough. Okay, so that would be a nice thing if I could be sure that that would be the case. However, well, you're quickly going to run into a problem if you hope that it is true. So here I just construct a simple example. So I take Hn to be essentially a sign, and the flow that the Hamiltonian flow that is going to make on the torus is well, this thing was just translated by a cos, and thus if I just take a straight line to be L0, and I take Ln to be the image by this Hamiltonian flow of L0, then Ln will be the graph of this cos of nx, and you can check that Ln indeed converges to L0. But obviously, you just need to look at a drawing to see that this does not converge into a Hausdorff metric, right? As n gets larger and larger, this thing's going to get wigglier, and from the point of view of the Hausdorff metric, Ln will converge to just like a solid rectangle, right? It's not going to converge to L0 at all, and thus it seems to be like that idea that maybe convergence in a nice symplectic metric implies convergence in Hausdorff metric is kind of like a bad one, right? It doesn't work. However, right, the point that I just mentioned is that it gets wigglier and wigglier. So what if I don't look at all Lagrangians, so I don't look at every sequences of the Lagrangian submanifold, but I'm only looking at those which respect some bounded curvature, okay? And essentially in that case, maybe I can have some hope that indeed it converges in Hausdorff metric, okay? So that kind of leads to a plan for today. I'm gonna need to set down some notation and some definitions regarding mainly Riemannian geometry and a little bit of lingua. And then I'm gonna basically state more formally a conjecture of Cornea, and then I'm gonna kind of explain morally how you prove such a thing. So let's begin with definitions. So let's first begin with some symplectic topology. Well, for now, it's mostly going to be symplectic topology notation, not definitions. So for the rest of the talk, I'm going to fix a symplectic manifold, and I'm going to fix an almost complex structure in such a way that the manifold is either closed or convex at infinity. And once this is fixed, I'm going to take this thing, which I'm going to just write L star M, and this is going to be the set of all close connected Lagrangians and M satisfying some symplectic condition star, and that condition star is either going to be, well, exact, so it means LEM is the set of all close connected exact Lagrangians in M. It could also be all weakly exact Lagrangians, or it could be all monotone Lagrangians, but if you do that, you do need to fix like a monotonicity constant and some mod 2 count of geomorphic disks. Okay, that's kind of details. What you should keep in mind is that whenever I write L star M, I'm meaning either all exact, all weakly exact, or all monotone, almost all monotone manifolds. And once M and L star is fixed, I'm going to take F and F prime, which are just two collections. I'm going to call them families, hence the F. And so I'm going to take two families in L star, and they have to respect this condition, right? It's not really important for now what it precisely means. They just respect some like kind of like topological condition with regards to their intersection. So once I have that, I can define what I'm going to call a J-adapted metric, okay? So concretely, a J-adapted metric is going to be, well, one of the metrics I've talked about, right? Concretely, it's going to be either the Lagrangian Hofer metric, the spectral norm, the shadow pseudometric, or it could be, oh, right now I'm talking in terms of pseudometry, sorry. Yeah, so the J-adapted pseudometric is going to be one of the things I've talked about. But it could also be something else, right? So that's why I wrote this big DF. It could be some of those weighted fragmentation pseudometries, which have been introduced by Biran, Cornea, and Zhang. Not all of them, but some of them. So there's a lot of possibilities. And whenever I have two J-adapted pseudometric, I can take the max, and I'm going to call that a J-adapted metric, right? And later on, I'm going to kind of prove that it's actually metric. So, and yeah, okay, yeah, okay. So what kind of like joins them all together? So right, so I've just given you like a grocery list of all the things it could be, but what does it actually mean to be J-adapted? Well, essentially it means that whenever I have two Lagrangians and I take a point on one of these two Lagrangians, I'm going to get a geomorphic polygon with boundary in L prime, maybe some additional Lagrangians which come from this fixed family, hence why you do need those families. And this holomorphic polygon is going to go through that point X, and it's going to have an area bounded from above by the distance between L and L prime. So this is kind of like what's the important property of J-adapted, well, pseudometric here, okay? And there's maybe like a little bit of a lie in what I've just said, which is that actually this is when L prime and all the members of family meet transversally. If they don't, this is up to some arbitrary small Hamiltonian perturbations of all the loss Lagrangians. So great. So this is J-adapted metric. Now we're going to go on to Riemannian geometry. So I fixed a J, I fixed the symplectic manifold, and thus I have a Riemannian metric, and thus I also have a Levi-Civita connection, obviously. So this is mostly a recall, obviously. I'm pretty sure everybody knows that.
Excuse me, may I interrupt you for a second? So could you, I didn't understand. So if, for instance, your metric is usual Hofer's metric on Lagrangians, so what is the role of these collections F and F prime?
Sorry, could you repeat? I missed the end of it.
So assume that we have DH. So in the case of DH, do you have collections F and F prime or not?
Well, essentially, No, I don't have them. Essentially, it would be the case where F and F prime are empty.
Ah, I see. Okay.
Yeah, that's a very good question.
And so they appear for this shadow pseudometrics, right?
Yeah, essentially, there are for those shadow pseudometrics, right? It's kind of like, yeah, I'm only introducing that because the same thing for the spectral norm. It would also just be empty families. So.
Okay, thank you.
That's pleasure. Great question. Right. Okay. So back to Riemannian geometry. So, and the second fundamental form, right? It's a thing which takes two tangent vectors to a submanifold and one normal one, and it kind of smooshes them together using the Levi-Vita connection. And essentially, right, what is calculated calculates the failure of the submanifold to be totally geodesic, essentially. And so, since this is right a linear application, I can use the Riemannian metric to take its norm. Well, there's a notion of its norm, and then I can just take the supremum of the norm at each point, and I'm going to call that the norm of the second fundamental form. And this is what basically what I meant at the beginning when I said curvature, right? This is what I'm going to call curvature. This is it's the norm of the second fundamental form of a submanifold. However, it turns out that for the proof, it won't be enough to just control the second fundamental form. I will also need another condition, which I'm calling epsilon tameness, okay? So say they have a submanifold L of M and some epsilon. L is epsilon tame if it respects this inequality. So this is kind of like, well, gibberish at first, if you just look at it, but basically what it means is that, well, you have on L, you have two distance function, right? You got the one, which is just the restriction function of M to L, but there's also the intrinsic distance function on L, which is the one that you get when you see L as a Riemannian manifold and not just a submanifold, and then you're looking at the geodesics in L, not in M, okay? So these two metrics in distance function will in general be different, obviously, and thus you kind of need a control to compare them. And essentially what the conditions here tells you is that on a small enough ball, you can compare the M and the L, okay? So this is just what it means. And this definition, it kind of appeared at first in another form as being just tame in a work of Sigorov, but it also has appeared more recently in work of Groman and Solomon, and in there it's named epsilon Levschitz. So there's a few names for that, slightly different definitions. Okay.
So this condition is not satisfied in the cosine example that you showed us, right?
It is not, indeed, because if you take two, I guess we can go back a little bit, yeah. Because if you take, say, two successive zeros, then the distance in LM is getting smaller and smaller, but the distance in L is always at least 2, right? That makes sense. Great, okay. And now that I have my two conditions, this norm on the second fundamental form and this epsilon condition, epsilon tameness condition, I can define subspaces, right? I can define the subspace of L star of all the Lagrangians which have bounded second fundamental form, and that not just the bound, but the bound is given by this big lambda, and also can define L star lambda epsilon, which is all the L in L star lambda, which are also epsilon. So this is just a bit of notation. Great. So now that all the definitions have been set down, we can actually state the conjecture and finally give some idea of what's going on. Great. So the conjecture, which is due to Cornea, is as follows. So you suppose that D is a J-adapted metric, and suppose that you have a sequence Ln in this L star lambda space. So if Ln is to converge to L0, which is also an embedded Lagrangian, it's important. So if Ln converges to L0 in this J-adapted metric, then it converges to L0 in Hausdorff metric. So this is kind of like the conjecture. This is like the formal statement of what I've said at the beginning. And what I've proven is that, well, if you add this epsilon condition, it's true. And furthermore, if you're in dimension 2, you don't actually need to add this epsilon condition. Essentially, the conjecture is true in dimension 2, and it's true in general if you add this epsilon tameness condition. So just a quick word before moving on to some, well, consequences of that. It's that, well, even though it is true that, well, the condition that Ln is in this L star lambda for a fixed lambda, well, that condition depends on J, right? If I change a J, the same sequence might not be in the corresponding L star lambda space. However, the condition that Ln is in L star lambda for some lambda does not depend on J, right? If I change my J, well, a sequence which has uniformly bounded second fundamental form will still have uniformly bounded second fundamental form. So actually, even though we're using a metric to define all of this, this is kind of like a symplectic property. So to be in such a space for some lambda is actually symplectic. Well, it does not depend on J.
Excuse me, may I ask you a question? So you have these two conditions, lambda condition and epsilon condition. Are they independent? So do you have an example where lambda condition holds and epsilon does not?
So that's a bit of an issue. I'm trying to prove that it's actually independent. I think it's actually also independent. It is for sure if you just like perturb J a little bit, but in general, I don't have a proof. I think it's true, but I don't have a proof.
Okay.
Thank you. Okay, so just a quick, okay. So a corollary. So I just have to recall this thing which is called the Pedomens stability theorem. So it's a bunch of fancy language, but essentially what it tells you is that if you have a sequence of nice spaces and the sequence converges, then for n large enough, these spaces will be homeomorphic to their limit. Okay, so this is just a bunch of fancy language. They converge to Gromov in Gromov-Hausdorff metric, to be fair. Okay, so their direct consequence of this theorem is the following corollary. Is that, well, if I have a sequence of Lagrangians which converges in some J-adapted metric to L0, and I know that L0 once again is embedded, then Ln is actually homeomorphic to L0 for n large. So essentially, adding these metric constraints allows one to say that near L0, everybody's homeomorphic. And obviously, when your J-adapted metric is the Lagrangian Hofer metric, that's not saying much. But when you're talking about the spectral norm or one of these shadow metrics or one of these other weighted fragmentation metric, that's kind of big, right? Because for shadow metric, you can be comparing things which are not even homotopic. So it's kind of surprising that actually, well, it's kind of nice that they are actually on some neighborhood, they have to be homeomorphic. Great. And now I'm looking at time and I'm essentially already done. So I'll be going real fast for the idea on how to prove it. So first thing first is the thing that I've talked about. The key property of these J-adapted metric is that, well, there exists some J-holomorphic polygons which have area bounded above by the distance between Ln and L0, right? Up to some arbitrarily small perturbation of these Lagrangian. Great, so you have that, and thus essentially what you need is a lower bound on these area. And the key for that is, well, a version of the monotonicity lemma. Okay, so essentially the monotonicity lemma tells you that if you have a ball which meets a geomorphic curve in the right way, then the area of the geomorphic curve has to be big enough, essentially, right? And the point is that you have to modify a version of the monotonicity lemma which appear in work of Sigurov, so that all the constants that appear only depend on these lambda and these epsilon. Great. So essentially, this allows you to give a lower bound on the areas which only depend on this lambda, this epsilon, and the distances between these point x and x prime to the other Lagrangians. And then essentially, you use this weird topological constraint on the intersections of the elements in your family to turn the dependence in these distances into a dependence on the Hausdorff distance, actually. And thus you get a bound which is something like constant times Hausdorff distance square is smaller or equal than the distance in the J-adapted matrix. And thus this is kind of direct, right? If you get something like that, well, if one tends to 0, the other has to tend to 0, and then essentially you're done. And yeah, and just finishing, essentially in dimension 2, you can do a trick which allows you to essentially use a better version of the monotonicity lemma, which does not depend on epsilon. And that's why in dimension 2, you can get rid of the epsilon. So I think that's going to be all. I'm a bit over 20 minutes, sorry.
That's okay. Thank you very much. Any questions?
I have a question, actually.
Yeah.
You said something, but do you actually have any examples of some Lagrangian conversion to some other Lagrangian which are not homeomorphic?
Something which would converge, which one? Well, no, actually, we expect that this should always be the case, essentially, even without, you could hope that even without these metric constraints, you would hope that locally everything is homeomorphic. However, it's kind of like hard to prove without those, if that makes sense. Thank you. Actually, yeah, so actually in the pseudometric, right, because in the shadow matrix, you also have pseudometric and you're taking the max of 2 pseudometric to get the actual metric. In pseudometric, that can happen, that something non-homeomorphic converges to something else. But in the actual metric, we don't expect that to be possible.
One issue is if your limit is embedded or not,
Mm-hmm.
and how you decide whether a limit or a sequence in this matrix, which is Cauchy, say, in this matrix, what type of limit it can have. So one thing Jean-Philippe showed is that a limit can be very wild if you don't put any curvature condition. But right, so that's not quite what you're asking, Augustin, but okay.
Yeah.
Do you have any kind of efficient bound, so relating d-metric and delta metric?
Yes, actually, I do. There's like, you can find a very explicit constant, a very explicit relation between the two metric. I haven't written it down, but it, as I said, it's something akin to constant with like an explicit constant, which depends on like metric invariance of m, and this lambda, this epsilon, times Hausdorff distance square, right? The square comes from the fact that you're using this monotonicity lemma with a square. And essentially, it's almost the same constant as here. I think there's a little bit of a difference, but it's essentially this J-adapted distance is bigger or equal than c times Hausdorff distance square. This is the bound that you get.
And so square comes from scaling, right, or not? Kind of in, I mean, it should be in which units is measured Hausdorff distance in meters, right? And
yeah.
Let's say Hausdorff distance in meters squared or something like this. So
Yeah, I guess indeed, in that sense, it comes from that. Yeah, indeed.
Okay, thank you.
Is it possible? Yeah, okay, please.
Maybe you were going to ask the same question. So if I understand correctly, I just want to just reviewing the results. The result is concerned the shadow matrix, but there was nothing that you said about the Hofer metric or the gamma metric, right?
Well, the point is that it works also for them, right? The point is that the result is stated for J adapted matrix, but in particular, it also works for the Lagrangian Hofer metric. It also works for the spectral norm in the case when you're taking F and F prime to just be the empty set, essentially.
Oh, I see. Okay. So the F and F prime made me think it was just so.
Yeah, it was just like to be a bit more general, so that so in order to encompassate those shadow matrices, because the result is a little bit more shocking for shadow matrix, I think.
Right. Well, it's just as interesting for the other ones. But so I've been thinking about a version of this. So maybe this implies it then for say homeomorphisms or diffeomorphisms. Does say convergence in gamma or Hofer for a sequence of diffeomorphisms, does it imply C0 convergence of the diffeomorphisms? Now it's not true without conditions. As you had, it's just not true without conditions. But so maybe there are some conditions, or maybe your result says something about that. That if you have a sequence of diffeomorphisms which Hofer converges, then it also converges in C0.
You mean symplectomorphisms, right? Or
yes, symplectomorphisms. Yeah.
Right. Well, you apply it for graphs. You apply his result for graphs.
Right. So, but then you get Hausdorff convergence.
Yeah.
Of the graphs.
But for graphs, Hausdorff convergence for graphs shouldn't be too far from what you want.
Right. So it's okay. So it.
So Subhan, I think the question is how many derivatives have to be controlled.
That's right. Yeah. That's it.
Right.
So two or three, I cannot do it by heart.
So then you have to control some. Right. It looks like you have to control certain derivatives before. Okay.
Yes,
but our guess was that you have to control two. But okay, it depends. It depends a bit of the context. So the other things that Jean-Philippe is trying to do is trying to look at the other situations in which these constraints make it easier to prove, sort of bounds and stuff. Yeah.
Okay, great. That's great. Thanks. Now, the other way around, if you have Hofer convergence, what can you say? If you have Hausdorff convergence.
If you have a Hausdorff convergence, well, you cannot. So well, obviously there's like dumb reasons why it could not work, right? If you have. Because you could have like things which are not, which are not like Hamiltonian isotopic, but which do converge in Hausdorff metric, and then obviously you won't be having a convergence in the Lagrangian Hofer metric, right? Because you're comparing things which are not even Hamiltonian isotopic, but they will still be Hausdorff metric. However, if you can eliminate that, I think. It should be true in some context. I don't have anything in that regards. I think there might be some results in the sense for the spectral norm. I think so. Correct me if I'm wrong, but I think that it can something that Shelukhin had done, which with in I think is in a paper in 2010, which gave some continuity result with barcodes or something like that. I'm not entirely sure about that, but I think that had something to do with Hausdorff, which with the other way around, essentially, that if you have convergence in spectral norm, then you would have convergence no, the other way around, sorry. If you have convergence in Hausdorff metric, then you would have convergence on spectral norm. But apart from that, I don't think that anything is known.
You have the Arnold, the nearby Arnold conjecture that one can